first, the bad news is that I still don't have your homework back. I hope I will get it back on Thursday. I will post today some solutions to the first homework. If you have any doubts about what I did, you can look at the solutions. Well, and as I said, I hope that on Thursday I will give you the homework back. Now, so the good news is today we are starting a really cool topic. It's called duality, and it's not that computational. And so I hope we won't cover 5 words like usually with lots of computations. And we'll have something to think about and something to wonder about. So let me start with formulating a problem, like we always do a linear programming problem. But then we'll do something different. We will not try to solve it, but we'll try to do something different. So the problem is maximize z, which is 3x1 plus 2x2 plus 8x3 subject to x1 plus x2 plus 4x3 small equal to 4, 2x1 plus 6x3 small equal to 5, 2x1 plus x2 plus 6x3 smaller or equal to 7. Okay, so that's the problem, and usually we would just, well, try to solve it using Simplex algorithm, start with 0, 0, 0, try to improve it at each step, and so on. That's not what we are going to do now. We'll discuss the following situation. Suppose somebody comes to you and tells, well, you know what, I played hard with these numbers, I spent the whole night yesterday and I found the following solution. I think it is actually the best. So, attempted solution, or rather attempted answer. Somebody tells you x1 should be 2.5, x2 should be 1.5, x3 should be 0. So maybe it's, well, I don't know, a program and you don't know the source code for this program, or maybe it's actually somebody who thought about the problem and recorded the answer without the solution, or, well, any other combination of things. But anyway, now you have this. And you computed for these values of x1, x2, x3. The value of z is actually pretty high. 3 times 2.5, 7.5, plus 2 times 1.5 plus 3, so plus 0, 10.5. So you stare at this answer, well, you think for a while, first of all, you check that it is a feasible solution, it does produce this value for z. But now you wonder, is it optimal? And I mean, you try a couple of other numbers according to x3, you can't find anything better than this 10.5. You start suspecting that it is optimal. And now you want to prove, you want kind of certificate that shows you, yes, this solution is actually optimal. I will never be able to find any solution which is better than 10.5. Okay, so here's one attempt how to proceed. Well, one attempt. Maybe let's look at all these inequalities and see from what these inequalities tells us about x1, x2, and x3. So let's say first inequality definitely tells me x1 is smaller than 4. Second one tells me it's smaller than 5 halves. Third one is smaller than 7 halves. So it is smaller than 5 halves. x2 you can also see that it's smaller than 4. x3 you can see that it's smaller than 1. Even 5 over 5, 5 over 6. And maybe then you can plug it into this value of z. Well, you will get some value. Z is smaller than 30. I didn't make this calculation, but it will not be that good. Okay, there is quite a huge gap between 30 and 10.5, so you start thinking harder, and you decide that rather than use this inequality separately, each one gives me some information, I'll try to combine them together to get some information about Z. So try to get inequality of the type Z is at most something. Try combining the constraints. What do I mean by combine? Okay, so Z is 3 times x1 plus 2 times x2 plus 8 times x3. Well, 3 times x1, I see that I can get it by taking first constraint, adding the second one, and I'll get exactly 3 times x1, plus some other stuff. Well, is it good enough? Well, so Z is 3x1, and the sum of first two constraints is 3x1, but plus only 1 times x2. Well, 1 times x2 is still smaller than 2 times x2, which is Z, which is a term in Z. Okay, so maybe I'll try to make up for this by adding the third constraint. It exactly has another x2. So, for instance, try adding the 3 constraints. And here's what we get. 3 times, oh no, sorry. Now it's 5 times x1. I add all 3 of those. 5 times x1 plus 2 times x2 and plus, well, 16 times x3. This thing is smaller or equal than 4 plus 5 plus 7, which is 9 plus 7, 16. Okay, so adding up the 3 constraints, you get that this expression, whatever x1, x2, x3 are, is smaller or equal than 16. Okay. On the other hand, you see quite readily that it is at most, that Z is smaller than this. Z only has 3 times x1, and here we have 5 times x1. Z has 2 times x2, which is also here, and Z only has 8 x3, and here there are 16 of those. And each one of these quantities is positive. Maybe it is worth reminding you that, well, we only deal with problems in standard form, which assume that all numbers are positive. So if to Z you add another extra 2x1 and another extra 8x3, you will get this quantity, so it will become bigger, and this quantity is at most 16. So now you have a proof that, well, the optimal value of Z, whatever it is at most 16. It's not as good as what we would like to have. We would like to have something like Z is always smaller or equal than 10.5. That would be ideal. But we are getting there. At least it's not kind of Z smaller than 30, it's Z smaller or equal than 16. Okay. So it's good. But, well, as you see, it's not good enough. We still have some room. We still might have Z equal to 12, might have Z equal to 14. We didn't exclude it here. Okay, so next idea is, let's try doing the same, but, well, using slightly different variation of these constraints. Maybe, let's take, to account for this 2 times x2 in Z, let's take 2 times the first constraint. And to account for the fact that Z has 3 times x1, and 2 times the first constraint only has 2 times x1, let's add, I don't know, half of the third constraint. Yeah?
If you have the first and the third, you get the Z as
Smaller than 11. Okay, yes. Even better. So, even better. And just first plus third constraints. What do we get? We did have 3 times x1 plus 2 times x2 plus 10 times x3, smaller or equal than 4 plus 7, which is 11. Wow, we are really, really close. And yes, indeed, z is smaller than this. It is 3 times x1 plus 2 times x2 plus, well, it is plus 8 times x3, and here we have 10 times x3. Okay, so this is indeed bigger than z, and this is always smaller than 11. So now we have just a very tiny gap, 0.5.
Can we just draw out like on the matrix to see if the z equation is a linear combination of the 3 other equations, and then just like what to do after that once we get the z equation is a linear combination of the other 3.
Okay, so the idea was, so here we have kind of a linear combination of the 3 constraints, first one plus third one, and what we use about it is that, well, z is, the expression for z is, well, not exactly the same as this one, but first of all, pretty close, and secondly, definitely small. That's what's important. So let's try to do it in, well, as suggested, in a more systematic way. Let's not just try to get the coefficients 1, 0, 1 for the constraints, let's just assume that there are some unknowns. And let's try to find these unknowns. So more systematically, and let's say y1 times first constraint plus y2 times second constraint plus y3 times third constraint. So here we attempted 1, 1, 1. Here we attempted 1, 0, 1. Okay, so let's see what we get. We'll get y1 times the first constraint, x1 plus x2 plus 8 x3 plus y2, oh sorry, plus 4 times x3 plus y2 times 2x1 plus 6x3 plus y3 times the third constraint, 2x1 plus x2 plus 6x3. And this is smaller or equal than 4 times y1 plus 5 times y2 plus 7 times y3. So we get this inequality. Usually, if you just try random values for y1, y2, y3, well, it is some inequality, but it won't tell you anything about z. But if the coefficient at x1 of z, which is 3, is smaller than the coefficient of x1 in this expression, and the same for x2 and the same for x3, then z will be smaller than this whole thing. So if the coefficients at xi in z are smaller than the coefficients in this expression, we'll have z smaller or equal than the expression. So if, let's start with the coefficient at 3, at x1. So if 3 is smaller than, what is the coefficient at x1 here? Let's see, it's y1 plus 2 times y2 plus 2 times y3. So this inequality is about the coefficient of x1 in the expression for z being smaller than the coefficient of x1 if you open the brackets here. Okay. Another thing we want is the coefficient of x2 to be smaller or equal than the coefficient of x2 here, which is y1 plus nothing and plus y3. And I also want the coefficient of x3a to be smaller than 4y1 plus 6y2 plus 6y3. So if this inequality is solved, then z is smaller or equal than this expression, which is smaller or equal than 4y1 plus 5y2 plus 7y3. So once again, if we take these constraints and combine them with some coefficients, take a linear combination of these linear functions, then we get this linear function. If this linear function happens to be bigger than z, which is written here, the linear function, the coefficients, are bigger than the coefficients in z. Then z is smaller than this linear combination, and this linear combination is smaller than the linear combination of the right-hand sides over there. Okay, so that's good, but it doesn't tell you exactly what numbers y1, y2, y3 to choose.
Can you just solve for that?
Okay, we could, but in general, there is a problem. The number of so in this particular case, yes, you're right. Here we should just probably solve it for y1, y2, y3. In general, the number of equations will not be the same as the number of unknowns. In this thinking, it will have kind of either no solutions or extra solutions, kind of infinitely many. So in general, you will not be able to. Wait a second. That's not the reason.
Yeah.
Okay, so
You have too many unknowns.
once again, in this particular example, because the number of variables and number of equations happens to be the same, and the number of variables and constraints happens to be the same, it is a good idea, but in general, say you have 100 variables and just 2 constraints. Then you'll try to combine the 2 constraints to get the objective function, and you'll never be able to do this. So in general, it will be impossible. So you're right, in this station it will work. And it's my bad that I came up with such an example. I didn't think about this. But in general, once again, in general, what we should try to do is to get the best possible bound here. So we already know that we can get 16. We already know that we can get 11. What we'll try to do is to see whether we can get this 10.5. In general, we'll try to get as small bound as possible. So now we'll try to get to the best possible bound by solving. Oh yes, and another thing. Even here, it's not. Yes, even here, it's not possible just to solve these system equations. So let me explain. Suppose you solve these system equations and you get that y1 has to be -5. isn't good for you. Well, to be honest, no. Because minus 5, if you multiply the first inequality by minus 5, it will reverse sign. So even here, it's, I mean, yes, you could be able to express z exactly as the linear combination of the constraints, but maybe one of the coefficients will be negative. And then you will not be able to use this inequality, because when multiplying by the coefficient by 1, they will reverse sign. So maybe it's, so I write it down here. We only use positive linear combinations, because only multiplying by a positive constant will not change the sign of inequality. Only use y1 bigger than 0, y2 bigger than 0, y3 bigger than 0. So once again, why can I not use minus 5 times first constraint plus 3 times second constraint? Well, if I multiply the first inequality by minus 5, it will change the sign from smaller equal to bigger equal. And then I won't be able to use it. So we only will use positive linear combinations. Okay, so let's try to find the best possible upper bound. Let's try to see how small this bound can get. So I'll try to find the minimum possible value of 4 by 1 plus 5 by 2 plus 7 by 3 subject to these constraints. Plus 2 by 2 plus 2 by 3 bigger or equal than 3. So does it work still?
Yeah. Can you point it to the board? Okay, yes, it works.
Okay, so try to minimize this upper bound subject to these constraints. y1 plus y3 bigger or equal than 2. And 4 times y1 plus 6 times y2 plus 6 times y3 bigger or equal than 8. And of course, y1, y2, y3, as we said, are positive. So if we solve this problem, we are guaranteed to exhaust this method to the very end. We'll find the absolutely best possible linear combination of these inequalities, the best possible way to combine them to get some upper bound on Z. Okay, so I promise that we will not do any computations. I mean, after all, this is a linear programming problem, and to solve it, well, involves using the simplex method, which, I mean, why have you thought so hard? I mean, we started with the problem, we didn't want to solve, now we get another problem. Well, so I'll tell you a solution of this problem, just one feasible solution. So, a feasible solution y1 is equal to 2, y2 is equal to 1/2, y3 equal to 0. So take 2 times the first constraint plus half times the second one. Okay, so we'll get what is the value of this function that we are trying to minimize? Our upper bound, 4 by 1 plus 5 by 2 plus 7 by 3. 4 times 2, 8. plus 5 times 1 half, 5 halves, plus 0, 10.5. And also, z is smaller or equal than 2 times the first constraint plus half the second one. So it is 3x1 plus 2 times the first one, 2x2 plus 2 plus 1 half, 4 plus 8 plus 3 plus 11 by 3, and it happens to be smaller or equal than, well, this equation, 4 times 2 plus 5 times 1 half, 10.5. Yeah.
That last line that you wrote, didn't that just follow from the inequality?
Yes, it does. I just rewrote explicitly what it means. So this particular solution to this problem will translate into this inequality about z. So we raised our previous attempt. Note that this inequality somehow is worse in this expression. It adds 11 times y3, 11 times x3, of course. But it is a little bit better on the right side. So you play with the right sides, and you get a better amount on the right side. Okay. So now, well, what we have is, I mean, from somewhere, from just, I don't know, somebody told you, two feasible solutions. One is a feasible solution to the original problem, another is a feasible solution to this problem about linear combinations. He didn't claim them to be optimal. He just said that, well, I worked hard with this problem, I worked hard with the other problem, and I guessed the following values. But now you have a certificate. You know that both values are actually optimal. How do you know? Well, for every solution of the first problem, z, the solution will be at most equal to any feasible solution of the second problem. And vice versa. Any feasible solution of the second problem will be bigger than any feasible solution.
Sorry, I was thinking of z is less than, or I got lost in there, the 4, 1, 1 plus 5, 1, 2 part. Where did that come from?
This.
Yeah, where did that come
Okay.
from?
So I was saying, let's look at the expression for z. It has 3 times x1. So let's take this expression for our linear combination and see what is the coefficient of x1 there. It happens to be this one.
Yeah.
So let's make this coefficient bigger than 3.
Okay.
Okay, let's do the same for x2 and for x3. So the coefficient of x2 and z is 2. Let's make it smaller than the coefficient here. Okay. If all of these are satisfied, then you know that z is at most equal to the linear combination. This linear combination.
Yeah.
And the linear combination, well, is more equal than the linear combination of the right-hand sides.
Yeah.
4 times y1 plus 5 times y2 plus 7 times y3. So overall, you get that z is smaller than this expression, and this expression is smaller than this. So it's exactly what we did with when we took y1 equal to 1, y2 equal to 0, y3 equal to 1, which means combine first and third constraints. But now it's just we don't combine them with coefficients 1, 0, 1, we combine them with any coefficients. And the important thing to check is that z is indeed smaller than the linear combination, which we compare just coefficient by coefficient. And then
Why did, so this lecture, like why did we do this in the first place? Why couldn't we just use like the simplex algorithm and test for x1 to x3? Why did we have to see it by this other method if it was a maximum number?
Yes.
Why couldn't we just use
So,
the simplex method on x1?
So the reason I'm not right now doing the simplex method and solving the original problem is because, well, I don't want just to get the optimal solution. So suppose I wrote a program, or, well, yes, let's talk about this situation. Suppose you code the program, and it solves for you any linear program, linear programming problem. But you're not sure whether your code is right. So it gets a problem, outputs some answer. Okay. Of course, given an answer, you can check quite easily that it's feasible. You don't have to solve systems of equations, just plug in the numbers, check that it's feasible, you can do it by hand. So that's good. So you check that the program took the original problem out, its output was this output. You plug it in, you see this solution is feasible. It's not a guarantee that it's optimal. How to guarantee that it's optimal? How to get some certificate that it's optimal? Well, the answer is like this. Take this problem now. Suggest it to the program. It will output some answer. Suppose it outputs this answer. It's very easy to check that it's feasible. Just plug it into here. But now something wonderful happens. You see that for this problem, you get a feasible answer which gives you the value of this function 10.5. For the original one, you get a feasible answer with value 10.5. But you know that you constructed these two problems to be related in such a way that for any feasible solution of the first one and for any feasible solution of the second one, you have this inequality. The first one is smaller than the second one. So you know that all feasible solutions of the first problem will be smaller than 10.5. You also know that all feasible solutions of the second problem will be bigger than 10.5. So now you know that both of these answers are correct. Both are optimal. For this, you did not actually solve the problem. You just used the solution from the program. You were not sure that it was correct. You just checked that both are feasible, that these problems are related in such a funny way, and now you have a certificate. You have a certificate that the output of the program was correct.
So this is just a checking method.
Mm-hmm. Yes. For now, yes. Later we'll have kind of deeper meaning to it, but for now, yes.
So when we're doing the questions, will we first use the simplex method, solve the first system, and then we would then check our answer using this system?
Okay, so for now, what you can do is, for now, of course, we just started, first of all. So for now, we just learned the following thing. Suppose you have some kind of oracle which tells you a supposed answer to any linear programming problem. If it tells you the correct answers to any problem, well, you can check that they are correct. That's all you can do for now. So, regardless of whether you solve it by hands or if somebody, your friend solved it by hands or whatever algorithm, well, we know how to check that the solution is correct.
But isn't this just as much work as the simplest algorithm? Like, is it
Actually, no.
This is less work.
This is much less work. We dedicate some of the work to somebody who actually tries to solve these problems, but now we have, how much work does it take to check that some solution is correct? Suppose we have a pair of solutions for the original problem and for this new problem. How much work does it take to check that they are correct? Well, just plug the numbers into the equations. There's basically very few computations in each case. Once you get the same answers, 10.5, 10.5 here and there, and the constraints are satisfied, you know that the solution was correct. So I'm not saying that we invented a new way to solve the problem.
So for this checking method, any feasible solution is like we don't have to solve for like an optimum or anything for the y1 equation.
Yes.
We just have to find as feasible solution.
Exactly. So if suppose that somebody told you, well, my guess for a feasible solution here is just 1, 0, 1. You check that the constraints are satisfied and the value of this function is 11. That's exactly what we had before. Okay, it's very good. Then we know that the optimal solution for the original problem, whatever it is smaller than 11. Well, if you manage to find a feasible solution for the original problem which gives you z equal to 11, then you are done. But somehow we didn't. So we tried harder and tried to find another feasible solution for it. But it is true that any feasible solution to this problem gives you an upper bound on all solutions for the original problem. So I did not solve this. I mean, I got the solution, the answer from somewhere.
Oh, okay.
So once again, I did not use just one guess, I used two guesses. First guess was a guess of answer to the first problem, second one was a guess of answer to the second one. But once I have both, I know that the original one was correct. So if I want to ask from the program not just an output of an answer, but an answer plus an easily verifiable certificate that the answer is optimal, well, that's what I'll ask. A solution for the original problem and a solution for this new problem. Once I have both in hand, I can easily by hands verify that both are optimal without solving. Later, we will have a way to know how to find these numbers given these numbers. So we won't even have to solve the second problem. But for now, well, we'll stick to just this situation.
Like, I understand the theory, I'm just kind of confused. Like, for the 2, half, and 0, like your answers, do you just keep on guessing until we get the right answer?
Yes.
So you didn't solve for it, you just keep on guessing.
Yes, exactly. So you should think about these answers as coming from some kind of, I don't know, alien whom you don't trust. I mean, he is extremely smart, but you suspect that he might be cheating. Well, so you get these answers from him, and you want to check that he did not cheat. And suppose that you don't want to actually solve the problem, and you really don't want to solve it. Well, then you ask him for this solution, he might have cheated. But it's very easy to catch him. You just take this solution, plug it into these constraints, you see that, well, at least he did not cheat, he didn't violate these constraints. You see that this solution does not violate the original constraints. You see that in both cases you get 10.5 as the value of objective functions. Now you know that he actually got it right. Okay? Okay, so let me formalize what we did in a little bit, well, in more general situation for any linear programming problem. So in general, given a linear programming problem, maximize C1 times X1 plus and so on plus Cn Xn. So that's just a very general form of a linear programming problem, subject to the constraints A11 X1 plus A1n Axn smaller or equal than 1, AM1 X1 plus AMN Xn smaller or equal than M. So I have n unknowns, m constraints, all of them are positive. So given such a problem, one can formulate what's called a dual problem. And this problem will be about trying to find so let me call this Z. Trying to find n upper bound on Z, like we did here, by doing some linear combination of these constraints, by making some linear combination of these constraints. So the dual problem is like this. Minimize. So we'll try to take these constraints, multiply first one by y1, second one by y2, last one by yn, and try to combine them. We'll get that the linear combination is smaller than v1 times y1 plus and so on plus vm times yn. So the linear combination of these constraints with coefficients y1 through ym is more or equal than this number. And we also want this linear combination to be an upper bound on z, which means we want the linear combination of, say, all the coefficients at x1 to be bigger than the coefficient of fx1 here. So subject to a11 times y1 plus and so on plus am1 ym bigger or equal than c1. And we'll do this for each one of these coefficients. The last one will tell you a1n times y1 plus and so on plus amn ym bigger or equal than the coefficient of xn here, which is cn. And once again, we'll take only positive linear combinations. y1 and ym will be positive. And let me call this W. Well, so this is just a definition, basically. Given a problem, any linear programming problem like this, of course you can formulate another linear programming problem. The question is how they are related. So here's the result. Theory. For any feasible solutions Z and W of these problems, Z is more or equal to W. So what is the meaning of this statement? If you find a feasible solution for the second problem, it gives you an upper bound on all possible feasible solutions for the first one. And vice versa. If you find a feasible solution for the first problem, well, you'll get a lower bound for all possible feasible solutions for the second problem. Suppose you can make these two bounds match. Then you know that you actually found the optimal solutions. So first of all, formulate kind of corollary to this. An additional statement: if we find a feasible solution to the first, it's called first problem. These z equal to some number. Let a feasible solution to the dual with W's some other number W star, and somehow it happens that these numbers are exactly the same, then both solutions, are optimal. So the first statement is something. It's, well, some inequality which is not completely evident. I mean, it is evident after our discussion about the combination of linear constraints, linear combination of the constraints. The second statement is quite obvious. I mean, if you manage to find some solution, some feasible solution here, and some feasible solution here, for which the values actually match exactly, then what did you find? Well, we found that any feasible solution of the original problem is at most some number, and you found a feasible solution which achieves this number. So it must be optimal. So the second statement is really easy. The first one, well, I will explain it once again. Yes.
Your C1 and Cn, are they not, they're not the same C1 and Cn there?
They are. They are exactly the coefficients of the objective function over there. So what I wanted to achieve here is, let me take a linear combination of these numbers, of these things. y1 times this expression plus y2 times the second one, and so on. What will be the coefficient fx1 in this linear combination? It will be y1 times a11 plus and so on plus ym times am1. I want this coefficient to be bigger than the corresponding coefficient of z.
Got it. Thank you.
So let me write down kind of formal explanation for why this inequality z smaller than W holds. I mean, we already, I think, understand it is intuitive. What we are trying to do is make a linear combination of the constraints such that each one of the coefficients in the linear combination will be bigger than the corresponding coefficient of the objective function z, and then z is smaller than the linear combination, and the linear combination is smaller than the linear combination of a1 to the m. Let's write it down. So explanation for z being smaller or equal than w is like this. I'll have an intermediate thing between z and w. I'll squeeze in the linear combination of these things. It will be y1 times a11 x1 plus a1n xn plus y2 times the second row a2n xn plus and so on plus ym times the last row m1 x1 plus amn xn. So on the one hand side, this is bigger or equal than what? So if I take the sum using the columns here, so it's x1 times this linear combination. But this linear combination is bigger than C1. So it's bigger than C1 times x1. And similarly for each one of these variables, Cn times xn. And this is exactly that. On the other hand, if you take the sums in rows, Well, this thing is at most V1. So it's at most y1 times V1 plus second row is y2 times V2 plus yn Bn, which is exactly W. So this inequality, once again, is about taking a linear combination of these constraints with coefficients y1 through yn, and then doing this kind of funny thing, taking a sum in columns. So combining the things according to the variable x, well, gives you this inequality. Z is smaller than this linear combination. Combining them according to the coefficient of y's, which means using the inequalities in rows, gives you this inequality. So it's smaller than W. Overall, Z is smaller than W. And in between, you have all these linear combinations. So let me give some names. The original problem is called the primal problem. The second problem is called the dual problem. So the original. Some names. The original problem is called primal. The one we start with. The second one, in terms of y's, is called the dual. The statement any feasible solution of the first one is smaller than of the primal is smaller than the any feasible solution of the dual is called weak duality theory. So this statement, you have two problems, they are related. One is called primal, the other one is called dual. For any solution of the primal, we know that it's at most as big as any solution of the dual. When this is called a weak duality theorem, let me explain why weak. Because it is actually quite weak. It only tells you, well, if you find a feasible solution for the dual one, it will be an upper bound for all feasible solutions of the primal. Will you be ever able to achieve some upper bound which is actually optimal? Will you be able to kind of close this gap between the smallest solution of the dual problem and the largest solution of the primal problem? Maybe the dual problem, I mean, think about the example which we started with. Suppose that somehow we tried and tried hard and only found the best possible value of W to be 11. And suppose that we tried and tried hard and only found the best possible value for Z to be 10.5. There is a gap of 0.5 and we can't close it by this method. Could it happen? Well, a priori it could. So we would get a certificate that kind of the optimal solution for the primal is at most 10.5, the optimal solution for the dual is at least 11, but it could be somewhere in between, I mean, between 10.5 and 11 could be 8. So this theorem is actually very weak. It tells you that, yes, you will be able to bound the optimal solutions from one side and from the other, but it doesn't tell you that you can always close this gap, that you can make those bounds actually match. So trying to work towards proving a harder statement, much harder statement. That actually, yes, you can always close this gap. You can always find a solution to the dual problem which achieves the same bound as the optimal solution for the primary problem. It will be called the strong duality theory. It will tell you that actually I didn't have to say that if we find a feasible solution such and so on, it will say there is always a feasible solution for the primal and a feasible solution for the dual, for which this holds, the actually match. Okay, so
Sorry, I have a question.
yeah,
So is it also true that if the system is not feasible, then the dual is also not feasible?
so we'll talk about this a little bit later. So we'll talk about the infeasibility and boundedness. So no, it could happen that the original problem is infeasible, but the dual is feasible. It could happen that the dual is feasible, but the dual is infeasible, but the original is feasible. But it's not possible. But at least we know that if the dual is feasible, the original is bounded. That's what we know for now. We'll discuss the other options later. Yeah.
So if one was unbounded, it would mean the other is not feasible.
So if
If Z was unbounded, then
Yes.
W is infeasible.
So if the original problem turns out to be unbounded, if you can make Z as large as you wish, you see that you will not be able to find any solution for that.
Oh, sorry. So the strong boundary theorem says if they're both feasible, then they will match, right?
Yes.
If they're both
Because what if Z is bounded, but Z was not the optimal solution?
If Z is bounded, but
Oh,
you
but that-
do not use the
You
optimal
cannot
solution,
use the optimal solution. What
then
happens?
you'll get still this inequality, but you will not be able to prove any kind of optimality because you didn't suggest an optimal solution.
Okay, so would W be enough? Like what would values of W will we get?
So suppose that you, for the original problem, you guessed a solution which gives you 9, value of Z which is 9. And suppose that you get the actual optimal solution for W which is 10.5. Then for now you know only that the optimal solution for Z is at most 10.5 and it is at least 9. You don't know whether it is somewhere in between this gap. Later we'll prove a strong duality theorem which tells you that if this value of W is actually optimal, you will be able to find a feasible Z with the same value. But for now we do not know this. Okay, so let's start working creatively towards this statement. How to find the optimal solution of given an optimal solution for the primal problem, how to find the optimal solution for the dual problem, and see that they actually match. So that's the goal for the rest of the lecture. We'll once again start with an example with just 3 equations. Basically, I'll copy the original example. So the motivating question is how given a solution of the primal to find the optimal solution of the dual. And once again, we will not answer this question completely. Today we'll talk about this thing. Suppose that you get not just a feasible solution for the problem, you get a full written out solution using the simplex algorithm of the prime. How can you extract the optimal solution for the dual without actually solving the issue once again? So that's what we do. So we'll start once again with an example. It will be this example, maximize z. I just copied the original one. So refer to the previous notes. 2x2 plus 3x3 subject to x1 plus x2 plus 4x3 small 4, 2x1 plus 6x3 small equal to 5, 2x1 plus x2 plus 6x3 small equal to 7, x1, x2, x3 bigger or equal to 0. So suppose that you solve this problem using the simplex algorithm, and in the end you find, well, the very last step was dictionary is as follows. x2 is 1.5 minus x3 minus x4 plus x5. x1 is 2.5 minus 3x3 minus 0.5 x5. x6 is 0.5 plus x3 plus x4 plus 0.5 x5. And z is 10.5 minus 3x1 minus 2x4 minus 1 half x5. So suppose that you work hard and in the end you get to this dictionary. So it tells you that z being 10.5 is the optimal solution for the original problem. The variables x5, x3, x4, x5, x1, x2, x3, x3 inequalities, x4, x5 should be x6. Oh, x6 is here, this base is just. Okay, yes. So x4, x5, and x6 are just the slack variables which you add here. So here we can say where x4, x5, x6 are the slack variables. x4 is, well, take the original thing to the first constraint, 4 minus x1 plus x2 plus 4x3. x5 is 5 minus 2x1 plus 6x3. And x6 is 7 minus 2x1 plus x2 plus 6x. Okay, so from here the question is, okay, so we solved completely the original problem. And now you are the, well, the unfriendly alien to somebody. You want to produce a certificate that your solution was actually correct. Maybe, well, maybe for the convenience of the grader, you want a solution to the original problem and a solution for the dual problem, which will be a certificate that your solution to the primal was correct, and you won't have to actually check all the steps in between. Wow, how cool. So, how to extract from this information a solution, actually the optimal solution for the dual problem? Yeah?
4 and 4, 5 and 6 times x 4, 5 and 6 should be equal to 0.
Can you see it again?
Y4, x4 should be 0.
Y, what is y4?
The new.
So we have the variables y1, y2, y3 for the three inequalities.
Oh,
And
well then y1, y2, and y3 times x4, x5, and x6 respectively should be 0.
right.
Because one of the constraints on either equation has to be met. Okay, you explain it and then
I understand.
Okay, that's fine.
Maybe I'll try to explain it.
Yeah, that's a good
Yeah,
idea.
okay, so let's look here. You see that the variables, the select variables x4, x5, and x6, they actually do involve something about the original constraints. And here you do have some kind of linear combination of x4 and x5. So maybe we'll be able to extract something about the linear combination from this final thing. So let's try. Log the expressions for x4, x5, x6 into z. Well, then you find that z is actually 10.5. Let's not change anything about x1, but let's actually write explicitly what we are subtracting here. Minus 2 times x4, so minus 2 times x4 is 4, plus 2 times this first inequality. x1 linear function, x1, x2, or x3. And then minus 1/2 of x5, so minus 1/2 times 5 plus 1/2 times this thing. x1 plus 6x3. So for now, as I said, I did almost nothing. I just took the expressions for x4 and x5, and x6, but I didn't use the x6, and plugged it into this expression for z. After all, this is just an equality, and these equalities I can use them. But now look what happens. Z is also, it has an expression in terms of the original variables. It's also 3x1 plus 2x2 plus 8x3. 3x1 plus 2x2 plus 8x3. So we have two expressions for z. One comes from the original description of what we are trying to maximize. Another comes from this very last line in our solution and the expression for the select variables. Yes?
Why is there a minus 2 times 4?
So it's because x4 is 4 minus something. So when I subtract 2 times x4,
Oh,
I subtract first 2 times 4, and then I add 2 times this. Okay, so first observation. What is the sum of these three numbers? So here I have something with the variables and something with numbers. 0. How did you get this? Did you actually add them up, or did you have some argument? Okay, you added them up. if you add these numbers up, you see that their sum is 0. Is it a coincidence, or is it something to be expected? No, it is something to be expected. It must have been 0, because I have equality between left side and right side. In left side, I have only expression in terms of x1, x2, x3, no free numbers. On right side, well, I have some parts with x1, x2, x3, and I also have parts with free numbers. So the free numbers should add up to 0, exactly to 0. If you plug in x1, x2, x3 equal to 0, you should have equality on both sides. 0 is equal to sum of these three numbers plus 0.
There should be minus 3x3.
Minus 3x3. Here.
Yeah.
Here.
Yeah.
Oh, so you say that this line was incorrect. It might have been. Yes, let me check. Yes, here I just copied it wrong. So please make a correction. The last line here is x3, and of course, once we plug everything back, you see that if it were x1, it can be wrong. The pointing over it. With x3, it's called with things like. Okay, so first thing that we observe is that 10.5 is actually 2 times 4 plus 1/2 times 5. Okay, another thing we observe is the following. This objective function z is, well, it's 2 times this linear function plus 1/2 times this linear function. Those come from the constraints. And then we subtract another 3 times the decision variable, 3 times x3. So if you just take the linear combination of these two constraints, we'll get some expression which is bigger than this. Every coefficient here is bigger than this. So we also observe that 2 times this constraint, x1 plus x2 plus 4x3, plus 1/2 times 2x1 plus 6x3, is always bigger or equal than, well, z, which was 3x1 plus 3x2 plus 8x3. The reason is, if you take this linear combination and then also subtract 3 times x3, you will get exactly this. If you don't subtract, well, of course, you'll get only something bigger. Well, so what does it tell you about the dual problem? If you take the linear combination of this constraint and this constraint with these coefficients, 2 and 1/2, you'll get, well, something which is feasible for the dual problem. That's this inequality. Each coefficient in this linear combination is bigger than the corresponding one in Z. And also you'll get something whose some feasible solution with value 2 times 4 plus 1/2 times 5, which is exactly equal to the optimal value for Z. It is optimal value in here. Well, conclusion. Thus, y1 which is equal to 2, y2 which is equal to 1/2, y3 is equal to 0 is a feasible solution for the dual once again. Why is it feasible? Because the linear combination of the constraints with these coefficients is bigger or equal than Z. That's exactly what we try to achieve. Linear combination of the constraints being bigger or equal than the original objective function. That's the formulation of the dual. and also with value of W equal to the optimal solution of the primal, i.e. 10.5. Okay, so now the question, how given just this one line to find a feasible solution for the rule for which the value of W is the optimal solution of the primal? Well, here's the answer. So x4, the stack variable for the first constraint, comes with coefficient -2. The dual solution for the dual solution will have y1 equal to 2. y1 is also about the first constraint. x5 here comes with coefficient -1/2. It is related to the second inequality. The dual variable related to the second inequality is y2. It comes with coefficient 1/2. And finally, x6, which you don't see here, there is a reason you don't see. It is a basic variable here, and it comes with coefficient 0 here. So I won't touch the third constraint at all. Y3 is equal to 0. So first of all, this worked in this problem. Second thing, it works quite generally. I maybe don't want to spend kind of last 3 minutes on explaining the kind of after thing, but this trick will work generally. Next time we'll start with formulating the same thing, but for a general problem, write the last dictionary and show that the coefficients of the set variables are exactly the best possible optimal solution for the dual problem.
So I'll always be wrong.
If there is no solution, you will be able
Have you made more progress on it?
I just